All right, hello everybody. I wanted to drop a brief video of glycolysis just to give you a general sense of why glycolysis is important, how it's different from the other metabolic pathways that we're going to talk about, and why it's a critical part of your everyday life. Of course, just by looking at the term glycolysis, I hope we can recognize the two words, the two root words that make it up. We've got glyco and lysis. Of course, lysis is just a cut, right? So we get out our scissors. We're going to cut something. What are we cutting? We're cutting sugar. And so glycolysis is nothing more and nothing less than the initial steps of how the body processes glucose processing. And this is one of the most rapid forms of energy that your body can create. So with that in mind, I'd like to just draw glucose real fast. We'll draw linear form. It's a 6-carbon aldehyde, which means that double bonded oxygen is terminal on carbon number 1. And it's covered in hydroxyl groups, these OHs. And then, of course, everything else is a hydrogen. So there's glucose. My question to you is simply this. Where is the energy? If I look at that molecule, I want to be able to see where the energy is. And if you watch my previous introductory video, hopefully you're thinking, well, the energy is in the transition of reduced carbon to oxidized carbon. But what does that mean? Well, if we look at the bonds, right? Reduced carbon bonds, these are carbon-carbon bonds and carbon-hydrogen bonds. But if we're thinking about oxidized carbon, we're looking at carbon-oxygen bonds. Because the electronegativity of that oxygen is higher than the carbon, oxygen essentially takes ownership over those electrons. And when we talk about oxidation and reduction, we're talking about the gain and loss of electrons. If you need a review of that, go back and watch that introductory video that I made on metabolism. Of course, what this means is that at the end of the day, we've got 6 carbons in glucose, and we can label them, right? 1, 2, 3, 4, 5, 6. When we're done with this molecule and we've extracted all the energy from it, that means that all 6 carbons will be converted to carbon in its most oxidized form, will be turned into carbon dioxide. And of course, we see this all the time. Every time I exhale, I'm breathing out carbon dioxide. Carbon dioxide is the byproduct, the waste product of metabolism. Now, I do want to note, this is not going to happen in glycolysis. So we'll put a little asterisk here and say, not during glycolysis. But glycolysis starts the process of carbon oxidation. Because this is all about carbons and the bonds that it's making, I think it's most useful, at least for an introductory explanation, just to focus on those carbons. So let's draw glucose again, simply as a 6-carbon molecule. Of course, it's floating around in the blood. I've got a blood glucose level between 80 and 100 milligrams per deciliter. And when I need to burn that carbon, or when I need to increase energy production and burn that sugar, I'm going to open up a door. This is my cell. And I'm going to let glucose come inside. Of course, because this is facilitated diffusion, if concentrations on the inside got high, even higher than they were on the outside, glucose is just as likely to go back out. Of course, I don't want that to happen. That I can't allow. So, the first thing that I'm going to do as glucose comes inside is I'm going to tag it with a phosphate group, and I'm going to attach this onto the end, to the number 6 carbon, generating glucose 6-phosphate. This has 2 purposes. Number 1, it starts the process of oxidation. Number 2, it prevents that glucose from leaving the cell, essentially keeping my glucose concentrations very, very low inside the cell because instead of glucose, now I have glucose 6-phosphate. It's a different thing. Please recognize, because this is a because this is an anabolic reaction, I'm building stuff, right? Anytime I build or assemble things, it takes energy. And so we have to recognize that this phosphorylation event is driven by energy consumption. In other words, I'm using ATP. ATP is the primary energy currency of the cell. ATP is giving up one of its phosphates and being converted to ADP. Now, hopefully you're asking, what are we doing, right? I thought the whole purpose here was to generate ATP, not to consume it. And in that argument, you'd be right. However, just like in real life, it takes money to make money. And that's what we're doing. That's why this is called the investment phase. Now, there are several steps here that we're not going to focus on. There's an isomerization to fructose and some other things, but we're not going to worry too much about that. We're just going to go through the primary steps associated with energy production or energy consumption. And so the next step we're interested in is another ATP being consumed, again, to make ADP as the waste product. Then it's going to transfer its phosphate to the number 1 carbon. This gives us fructose 1,6-bisphosphate. All of this leading up to this next event, which is the lysis. I'm going to cut this molecule in half. And that, as we zoom out, is going to give me 2 similar but distinct molecules. Dihydroxyacetone phosphate on the left, and this one, very important, glyceraldehyde 3-phosphate, or G3P as an abbreviation, on the right. Now, because our sole purpose is to generate ATP right now, we're going to take this dihydroxyacetone phosphate on the left, and we're just going to isomerize it, and we're going to turn it into glyceraldehyde 3-phosphate. There are uses for dihydroxyacetone phosphate, things that we don't want to discuss right now. So we're just going to turn it into glyceraldehyde 3-phosphate, which means that everything we do from here on out is going to be times 2, because we got 2 of these molecules. And all of this, as I mentioned before, because we consume 2 ATP, right? We consume that ATP, we consume that ATP. This is called the investment phase of glycolysis. What we want to do now is get our money back. So let's go out to the payoff phase. This next step is an interesting one, and one of the most important steps in glycolysis, because we produce a molecule called 1,3-bisphosphoglycerate, or for short BPG, 1,3-BPG. And you can see why it's named that, right? It's phosphorylated on both the 1 carbon and the 3 carbon. This step is important for a couple of key reasons. Number one, even though we added a phosphate to it, this didn't take energy. I did not use an ATP to get this phosphate. Rather, I was able to use an inorganic phosphate. Now, there's some manipulations that the cell does to make this a spontaneous reaction. Just recognize I don't need ATP. What I do need, and this is an introduction to a very important molecule, I do need an NAD+, nicotinamide adenosine dinucleotide. This is a derivative of vitamin B3 and is, because it's a vitamin, we consider this a coenzyme. It doesn't have enzymatic activity, but it is required for the enzyme to do its job. When we think of coenzymes, what I want you to think of is this. A coenzyme is a taxi cab. It moves things from one point to another. And for NAD+, this specific thing that it moves, super important. It's moving electrons. And we talked in the introductory video the idea of redox reactions. This right here, this, put a star. This represents a redox reaction, REDOX, oxidation reduction. NAD plus is going to come in and steal electrons from a carbon and be reduced to NADH. The difference between NAD plus and NADH? NADH is a taxi with electrons loaded on the inside of it, whereas NAD plus is an empty vacant taxi. This is a super important energy step because those electrons are high potential energy electrons that we can use to do work later in the metabolic process. All right, now the next couple of steps, this is where we're going to really start to generate some ATP. We're going to take this phosphate and transfer it to an ADP to generate ATP. We're going to take this phosphate and transfer it to an ADP to generate ATP. Both of these are examples of what we call substrate level phosphorylation. Substrate level phosphorylation just describes the transfer of a phosphate from one organic molecule to another. Whereas oxidative phosphorylation, which we'll see in the mitochondria, this is when I take an inorganic phosphate and I smash it together with an ADP. It's a slightly different process. But at the end of the day, we're making ATP, and that's what we want. Of course, there's a couple of steps in here that we don't need to name. And at the end of it all, we've got a 3-carbon molecule, no more phosphates on it, and this is called pyruvate. And that brings an end to glycolysis. So if we zoom out and look at the big process, we've got the investment phase early on. We've got the payoff phase here. The investment cost 2 ATP. Well, what do we get in return? For the payoff, we got an NADH, but remember, everything that you see here happens twice because we had two glyceraldehyde 3-phosphates. So for the payoff, I get 2 NADH. I generate 4 ATP. And hopefully you can see that, right? We have this ATP times 2. We have this ATP times 2. So that gives me my 4. But because it cost me 2 ATP in the beginning, I have to subtract those 2 ATP out if I'm looking at net production. And so it's easiest to think about it as 2 ATP. But remember, this is net ATP generated. But this allows us to follow a rule of 2s. And finally, 2 pyruvate. Glucose came in, we cut it, we oxidized it. That redox reaction is very, very important. And in the process, we were able to make a couple of ATP, and we've got a couple of electrons that are ready for work in a future process. That's glycolysis. Now, a couple of things to note when we think about glycolysis. First and foremost, we'll put a star down here, no oxygen required. That's what sets glycolysis apart from everything else. Glycolysis doesn't use oxygen and can run completely anaerobically. When we think about the Krebs cycle, beta oxidation of fats, electron transport chain, all of that requires oxygen for reasons that we'll describe later. This one, no oxygen required. And so that's why we call fast twitch muscle glycolytic muscle, because it's quick, it's powerful, but without oxygen, it doesn't have a lot of endurance. The last thing we want to add to this conversation is just an understanding of what we can do with this pyruvate. Pyruvate as a molecule looks like this. right? We can see that it's a 3-carbon molecule. What do we do with it? Well, I want you to recognize that there are still carbon-carbon bonds in there, that also carbon-hydrogen bonds, so both carbon-carbon and carbon-hydrogen bonds that can be oxidized for energy, right? We can steal more electrons from this molecule. So we don't want to just throw it away. What happens next is, for the most part, dependent on the status of the cell. So what to do with pyruvate? Well, I've got two choices. I can reduce pyruvate to a molecule called lactate. Or you might be familiar with lactic acid. It's the same thing. So I can reduce it to lactate, or I can oxidize the molecule to acetyl-CoA. Of course, in the form of acetyl-CoA, that could then join Krebs cycle, and I'm going to get a lot more ATP, a lot more energy from that process. So this is the route, pyruvate oxidation to acetyl-CoA, that's going to give me the most available energy. It's going to allow me to really burn through all of those carbons. What's the molecular switch that decides whether we reduce or oxidize it? Well, the molecular switch is the presence or absence of oxygen gas. So, in the presence of oxygen, I can enter the mitochondria, and that's where this oxidation is going to take place. In fact, that's why this oxygen is a molecular switch, because once we get inside mitochondria, everything that happens in there is dependent on oxygen. So if I have oxygen, then I can oxidize pyruvate to acetyl-CoA, and we're good to go. However, if I don't have oxygen, then the mitochondria is essentially shut down, and I have the chance to reduce to reduce pyruvate to form lactate. Why? In reality, lactate in and of itself isn't that important. If we follow that lactate, it's going to go into the blood. It's going to be brought up probably to the liver, where it's going to actually just be turned back into pyruvate. And then I'm going to use that pyruvate to run essentially glycolysis in reverse, gluconeogenesis, to make glucose, and then I'm going to store all of that glucose in the form of glycogen. So 60 to 70% of all of your glycogen storage on a day-to-day basis actually comes from lactate. So we recognize that it's a storage form. There's still a lot of potential energy in it. But why go through the process of having this reduction phase in the first place, from pyruvate to lactate? Well, it's not because I care about lactate, but because I care about the redox reaction that takes place. Remember, if we go back and we look at the conversion of glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate, this was the one redox reaction in glycolysis, and it produced NADH. But if the mitochondria is shut down because I don't have oxygen, then that NADH becomes not very useful. Those electrons are used to run the electron transport chain. But if the electron transport chain can't run because there's no oxygen, then NADH is basically foreign, worthless currency. So here, what do? We take that NADH and we use those electrons to reduce pyruvate back to lactate. What that means is that NADH is oxidized back to NAD+. This is the purpose for lactic acid fermentation, to regenerate my NAD+, because that has to go back up in order to continue to run glycolysis. In other words, if I don't do that, then I turn all of my NAD+ to NADH, but I can't turn my NADH back to NAD+ without the mitochondria. And then I'm stuck. I end right there at glyceraldehyde 3-phosphate. After the investment phase, but before the payoff phase. That's a bad place to be. Lactic acid fermentation allows me to recycle back to NAD+, which is necessary for that step from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate to continue so that I can produce the ATP in the subsequent steps. So, in summary, glycolysis is the initial steps of processing glucose. It's broken up into two steps, an investment step that costs 2 ATP, and then a payoff step where I see a redox reaction to give me NADH, and I generate ATP, and then the end product is pyruvate, which still has some potential energy left in it. Once glycolysis is ended, what I do with pyruvate is dependent on the presence or absence of oxygen. In the absence of oxygen, I reduce the pyruvate to form lactate. This is lactic acid fermentation. The purpose of fermentation is to recycle NADH back to NAD+ so that I can continue to run glycolysis, that redox step, from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. However, in the presence of oxygen, the mitochondria allows me to recycle my NADH back to NAD+, so that's not a concern. As such, in the presence of oxygen, I can further oxidize my pyruvate to acetyl-CoA, which is then going to enter the Krebs cycle for its final processing. The key feature of glycolysis is that it's quick and powerful because it does not require oxygen. That's what separates it from the other metabolic processes, and that's why glycolysis is so fun.